Welcome to this web note that I prepared as an application of all these fundamental theorems and properties of the linear operators, and as an application to the special case of invertible operators. Let us first recall some basic facts about invertible operators. Number one, though some of them we saw them before, but let me just redo it again just for the sake of refreshing. So let U and V be two vector spaces. A map A which goes from U to V. I mean, these definitions do not have anything to do with the vector structure of the spaces. It's just because we're in the setting of vector spaces, that's why I'm considering this, okay? Number one, A is said to be injective or one-to-one if and only if for any U, V in U, A of U equal A of V will imply U equal V. 2. A is said to be surjective or onto if and only if for every V in V, the image set, there exists a U in U such that A of U is equal to V if and only if A, the image set of U, is equal to V. Okay? And finally, we say that A is said to be a bijection or invertible if and only if A is injective and surjective. Okay. It is easy to see that for any map A which goes from U into V, we consider naturally another A, we call it A, but it's different map which goes from U to A of U, okay, the image set, and this map is onto if we restrict, okay, or surjective. Okay, by definition. So we still write it as an A, but this map is a little bit different from the original one because the target set is not V, the entire space V is a subset of V, which is the image of A. Okay, if A, I'm sorry, not A, if the two spaces, if A is a linear operator, okay, if A is a linear operator, then we have two natural subspaces associated to A. Number one is what we call the null space of A, and that's n of A equal to the kernel of A equal to the vectors U in U such that A of U equals 0. And of course, the 0 here is the 0 vector of V. So this is a subspace of U and is a subspace. Okay? 2 is the range of A as defined before. This is A R of A equals A of U, U in U, and this is a subspace of V. R of A is a subspace. It's a linear subspace. It's a subspace of V. Okay? It is easy to check in this case, to check that if A is one-to-one or injective, then the null space of A is reduced to 0. The converse is true as well. So a linear map is injective if and only if the null space is reduced to 0. Okay? If the null space of A is not reduced to 0, it's a subspace so it has 0 but it's bigger than 0, then in this case there is a natural way of coming up with one-to-one map from A. So the map A hat defined from the quotient space into V by taking A of U is one-to-one. Injective. First of all, before we proceed a little bit more, we can ask, is it well defined? In other words, what if I take another element in the class of U? So if V belongs to the class of U, then U minus V belongs to N of A, which implies A of U minus V equals 0, or A, because of the linearity, A of U equal A of V. So you see, the value here, this value here, is independent of the element we're taking in the class. Okay? And that's why this function A hat is very well defined. Now, why A hat? First of all, A hat is linear, so it's easy. It is easy to check that A hat is linear. And is one-to-one, injective. Indeed, if A hat of the class of U is equal to 0, so I'm trying to find the null space, okay? Then A of U is equal to 0. Then U belongs to the null space of A, and in this case, and therefore, we have the class of U equal the null space, okay? Which is the class of 0, which means that the null of A hat is exactly the class of 0, which is the 0 vector of the quotient space, which means that A hat is one-to-one. So this gives us a natural way of defining a map which is one-to-one very naturally from, but we have to use the quotient spaces. Okay? Great. So now let's go back to the case of bound linear operators and being seen for the invertible ones and see some of their properties in the light of the fundamental theorems that we have. So first of all, a direct application of the open mapping theorem. So the following result is a direct application of the open mapping theorem. Let U and V, let U, V be two Banach spaces. Let A be a bounded linear operator from U to V. Assume that A is invertible. Assume A is a bijection. A is a bijection. So we do have an inverse. Then its inverse is a bounded linear operator. Which means that A inverse belongs to B, but be careful, the A inverse goes from the other way around, from V into U. Okay? So here, proof, it is easy to see that since A is linear, then the inverse is linear. So the linearity is very easy, just the properties of A combined with the definition of the inverse, and we get the linearity. The problem here is the continuity or the boundedness, okay? So we only need to check that A inverse is a bounded operator. Since A is a bijection, then A is surjective, because we need this assumption in the theorem of the in the open mapping theorem. So we get there exists, and of course we're assuming that U and V are both Banach spaces, there exists alpha positive such that for every V in V, there exists U in U such that A of U equal V, and the control norm of U less than alpha norm of V in V. Okay? Clearly, U is equal to A inverse of V, so we have the norm of A inverse of V in U less or equal than alpha norm of V in V. In other words, we have A is bounded and the norm of A inverse is less or equal than alpha. Remark, we can also use the topological characterization of continuity, because since A is an open map, then A inverse is continuous. So we could have used a direct proof using by the topological characterization of continuity. So in other words, the inverse of a closed set is closed and the inverse image of an open set is open. That characterizes continuity on the entire set. So we could have used it because A is an open map to show in fact that A inverse is continuous. Next, I would like to take a very nice example. Okay, the Carl G. Neumann series. This is extremely useful for the people who are studying potential theory, for example, and also spectral theory, etc. So it's very, very interesting. In any case, let A be a bounded operator, BUV, and V and U and V are two Banach spaces. Let us assume that in this case, assume that V is equal to U, because we're going to use the composition of the operator A, and therefore, just to make it easy, we'll assume that V is equal to U. So A is a bounded operator on BUU, which we said we'll write it as BU. Okay? Then A to the power n, which is A composed with A n times, is in BU. It's a linear bounded operator, and the norm of A to the power n is less than the norm of A to the power n. Note that we'll always take I to the power 0 to be the identity equals I from now on of U. Okay? And its norm is equal to 1, so there is absolutely no confusion. Let A be a non-zero operator, okay, in BU. So of course this means that the norm of A is strictly positive. And let us consider, let lambda be a real number such that absolute value of lambda is bigger than the norm of A. Okay? And let us consider now the operator Bn for n greater or equal than 1. Let us introduce Bn equal 1 over lambda sigma of 1 over lambda to the power k, A to the power k, k from 0 to n. So clearly for every n greater than 1, Bn is bounded and belongs to Bu. So it's a linear operator which is bounded. Okay? Moreover, we have the norm of Bn minus Bn. Because I'm going to need some space, let's go right here. The norm of Bn minus Bn equal 1 over absolute value of lambda, the norm of sigma 1 over lambda to the power k, a to the power k, from m plus 1 k equal m plus 1 to n, and this is for every n bigger than m, for any n greater than m greater than 1. Okay, so using the properties, which implies the norm of Bn, where n is bigger than m, under the same assumptions, this is less or equal 1 over absolute value of lambda, sigma 1 over absolute value of lambda to the power k, norm of a to the power k, k from m plus 1 to n. Okay, good. On the other hand, since absolute value of lambda is bigger than the norm of a, then the positive series on the real line, positive series, sigma of the norm of a over lambda, absolute value to the power k from 0 to infinity, is convergent. Therefore, this will imply that Bn is Cauchy, is a Cauchy sequence. So now if we assume that U is a Banach space, okay, then in this case, so if we assume U is a Banach space, then Bu is a Banach space. Which implies, so the limits of the Bn's exist. So there exists B, an operator in Bu, such that limit of the Bn's is equal to B from n when n goes to infinity. And as you can see, the Bn's are just the partial sums of a series. In other words, that B is the total sum of the series, 1 over lambda, sigma of 1 over lambda to the power k, a to the power k, k from 0 to infinity. So we do have a convergent series. Okay. Now let us see some of the properties of this operator B. So let us take, so B is the limit of Bn. So before we move on there, let's take, we have, okay, note, if we take lambda I, the identity of U, times the Bn, okay, then this is equal to sigma of a to the power k over lambda to the power k minus a to the power k plus 1 over lambda k plus 1 from k equal 0 to n, which gives equal I minus 1 over lambda n plus 1 a n plus 1. So it's clear that the norm of 1 over lambda n plus 1 a n plus 1 is less or equal than 1 over absolute value of lambda n plus 1 norm of a to the power n plus 1, or norm of a over lambda to the power n plus 1. And since lambda is bigger than norm of a, this will go to 0. So since we have this, limit of this, the norm operators in BU is equal to the 0 operator in BU when n goes to infinity in BU. This is operator limit. Okay, so this gives us that the limit of this sequence of operators is equal to 0, and the continuity of the composition, continuity of the composition of operators, composition, okay, will give us, I'm talking from here, we'll get at the limit will imply that lambda I minus a times b is equal to I. Okay, so this tells us what? That, so conclusion, lambda I minus a is invertible, so it is a bijection, is invertible, and its inverse, lambda I minus a inverse, is equal to b equal to 1 over lambda sigma 1 over lambda to the power k equal a to the power k from 0 to infinity. So we have a very beautiful way of writing, and not only that, we have also that the norm of this operator lambda I minus a inverse, okay, is less or equal than 1 over absolute value of lambda sigma from k equals 0 to infinity 1 over absolute value of lambda k norm of a to the power k, and if we use the geometric series from real line, this is equal to this 1 over 1 minus norm of a over modulus of lambda, which is equal to 1 over modulus of lambda minus norm of a. Okay, so in particular, we have if the norm of a is less than 1, one can take lambda equal 1, and we get that I minus a exists, so we get I minus a inverse exists, and norm of I minus a inverse is less or equal than 1 over 1 minus norm of a. Oh, of course, we have still the same identity that I minus a inverse is equal to sigma of a, because lambda is equal to 1, to the power n from 0 to infinity, which is I plus a squared, etc. keep in mind the powers here are the composition, so it's not, this should not be understood as as some kind of product. This is the composition that we're talking about. Okay. As an application of this, if we take C equal I minus A, okay? So A is equal to I minus C, and the condition on A before implies then, so we must have, so if norm of I minus C is less than 1, okay, so we can use, because it's going to be the same as before, that the calculation that we just said, we said C inverse exists, it's equal to sigma of I minus C to the power n from 0 to infinity here, okay, and the norm of C inverse is less or equal than 1 over 1 minus the norm of I minus C. So I'm just rewriting what we just found before, okay? Next, let us extend these little calculations, algebraic calculations on this calculus on operators, on bound operators. Let U be a Banach space again. And V a normal vector space. Okay. Let A0 be a bounded linear operator from U to V, such that A0 minus exists and A0 inverse belongs to VU. So it's a bounded linear operator, okay? So in this case, for any A in BUV, we have A0 inverse A, which belongs to BU. Okay? Because A goes from U to V, A inverse 0 goes from V to U, so this operator, this composition here, will go from U to U. So, the calculations we just did will imply that if the norm of A is less than 1 over norm of A0 inverse, then the norm of A0 inverse composed with A will be less than 1, okay? And in this case, we can use what we just said, so I plus minus A0 inverse composed with A is invertible, okay? Okay. Clearly, the composition between two. Moreover, we have. Let's keep the. Moreover, we have the norm of I plus minus A inverse A inverse. It's going to be less than 1 over 1 minus the norm A. Okay, A0 composed. I mean, I'm going to drop this composition because it is understood that when we take the product, it means composition. Okay, this is just the case when we did it with the C. Okay, so in this case, we have, if we take B, set B equal A0 time or composition with I plus minus A0 composed with A composed with A, then B inverse is equal to I plus minus A0 inverse composed with A composed with A0 inverse. Okay? And the norm of B inverse is going to be less or equal the norm of I plus minus times the norm of this one, which gives me the norm of A0 inverse, over 1 minus the norm of A0 inverse composed with A. Which is less or equal than the norm of A0 inverse over 1 minus, and since this one is less than the norm of A0 inverse and norm of A, then this one will be bigger. Okay, so just a little bit of algebra. Theorem. Let U be a Banach space and V be a normed vector space. Okay, let A0 be in BUV such that A0 inverse exists and is bounded. Okay, so let A be in UV, a bound operator from U to V, such that the norm of A is less than 1 over the norm of A0 inverse A. Then B equal A0 plus minus A is invertible, okay, and B inverse is bounded with control over its norm. Norm of B inverse is less than norm of A0 inverse over 1 minus norm of A0 inverse norm of A. Okay? Let's go back to B. I want to go back to the operator B. So B was equal to this. Okay? If we put this, if we develop it, we get A0 times the identity map plus minus linearity of A0. A0 times A0 inverse times A, and that is A. So the operator B, in fact, is just A0 plus minus A. Okay? So we have this theorem. As an application of this, so that's what we proved before, as an application, we get the following result. Theorem. Let U be a Banach space. Okay, the subset invertible of U. So these are of BU. So I'm looking at invertible bounded linear operators, subset of bounded linear invertible operators defined on U is an open subset, is an open subset of BU. Be very careful. Uh, Invertible of U is not a subspace of BU, okay? Because if you take the identity map, it is invertible. If you take minus the identity map, it is invertible. But if you add them, you get the zero map, which is not invertible. So the invertible mappings of U does not give a linear structure to invertible of U. But it gives you a ring structure if you take the composition. Okay, so we have, yes, we don't have a linear structure, but we do have an algebraic structure that I'm going to avoid to talk about it here. So let us just first prove from a purely topological point of view that we are dealing with an open set. Okay, so prove, and this is just direct application of the previous theorem. Let A belong to the invertible of U. We want to show, let us prove that A is an interior point of the invertible of U. So A is invertible. Okay. So the norm of A is positive and the norm of A inverse is also positive. So both of them are not equal to 0. And let B in BU such that the norm of A minus B is less than 1 over the norm of A inverse. Okay? So we know that in this case we get the norm of A inverse A minus B is equal norm of I minus A inverse B, and this will be less than the norm of A inverse times the norm of A minus B, which is less than the norm of A inverse, which is equal to 1. So this norm of this operator is less than 1. So from the previous results, we conclude that the operator A inverse B is in of U, so it's an invertible operator. Okay, and since B is equal to A times A inverse B is also invertible. So the open ball, this tells us what? That the open ball centered in A with radius norm of A inverse is in the invertible set of operators of U. So A is an interior point. So we found the ball, an open ball, and this tells us that any point in M of U is in fact an interior point of view. Therefore, info view is an open set, and this completes the proof. The next result has something to do with first is what we call the spectral radius of an operator. So here, let's take a definition here. Let A belongs to BU, where U is a normed vector space. Okay, so we can consider, we know that A to the power n, or composition of A n times, is bounded operator, as we said earlier. So in this case, we have the norm of A to the n is less than the norm of A to the power n. This is for n greater than 1, factor 0, doesn't matter. And in this case, if we take the nth root of the norm of A to the power n, is going to be less than when n is greater than 1, because we're going to divide by 1 over n. Okay, so lim sup, so this quantity here, this sequence here, is bounded. So the sequence nth root of the norm of A to the power n is bounded. Okay. So the next theorem, study this sequence a little bit. Theorem. Okay. Let A belong to BU, and U is complete, is a Banach space. Do we need Banach space? We'll see that in fact we don't need Banach space, we just need normed vector space. It's very interesting when you have a proof of something and you see, did I use completeness or not of the space? So either you add it or you don't add it. We'll see. Then R of A equal limit of the nth root of the norm of A to the power n exists. So we do have a limit. So keep in mind, as I said, the sequence is bounded. Okay, the sequence of this sequence of numbers is bounded. It doesn't mean that you do have limits. So, but the theorem says that if we are in the case of a bound linear operator, then you have a limit. Okay. And what's interesting is that, and moreover, keep in mind that R of A, as we said before, for n greater, because we're looking at the limit when n goes to infinity, is always less or equal than norm of A. Okay. Moreover, if R of A is less than 1, okay, then the series A to the power n from 0 to infinity is convergent. Okay, so keep in mind, I already took off the Banach spaces. So we'll see in the proof whether we need it or not. Okay, so let's move on. Okay, and we'll see. If we need it, we'll come back, correct the theorem, and put Banach. If not, then we don't have proof. Keep in mind that if the norm of A is less than 1, then the norm of R of A is less than 1, because R of A is less or equal than the norm of A. Okay, so we may have norm of A bigger than 1, but the radius of spectrum of A, R of A, is less than 1. So it's very interesting. So a little bit richer, in fact. The conclusion, when norm of A is less than 1, we already did it, and we know that. Okay, so once the series is convergent, okay, we know that what's going to be the sum. The sum is just the inverse of I minus A. We did the calculations before, so we know, in fact, that the last conclusion, and I minus A inverse, this one we already did the calculations before, so we don't need to keep on going this. The proof is still the same. So, proof. So here, let us take, so we don't have the limit, we don't know that the limit exists. So first let us prove that the limit exists. So we take R of A to be the infimum of the nth root of the norm of A to the power n. Okay? So that's infimum always exists because the sequence is bounded between 0 and norm of A. So now let epsilon be positive. Let epsilon be positive. And there exists M such that R of A is going to be less than norm of A to the power n, less than R of A plus epsilon. Definition of the infimum. Now let n be greater than m. If we take the division of n by m, we get there exists k, n, l, n integers such that n is kn m plus ln, which is the remainder. We know that ln is going to be between 0 and m minus 1. Now let m equal the max of the norms of 1, norm of A, etc. till we reach A to the power m minus 1. Okay? So these are finite operators, so they are all bounded. So we have that maximum, for any n greater than m. We have norm of A to the power n to the power 1 over n. This is less or equal. Of course, it's equal, but so let's put it equal just for the sake of A to the power k n m plus ln 1 over n. Okay, which is less or equal by composition norm of A k n m to the power 1 over n, norm of A ln to the power 1 over n. So this is less or equal. So this part here, okay, is less than m, because this one of ln is between 0 and minus 1, so it's one of the ones that gives you the definition of m. So this is m to the power 1 over n. And now we go to norm of A to the power m to the power kn over n. Okay, and this is equal m 1 over n, norm of A to the power m to the power 1 over m, and then we have m kn over n, which is equal m 1 over n, norm of A to the power m to the power 1 over m, and here we have 1 minus, it's going to be n minus ln over n, which is less. Now m, let's keep it equal one more time, and then we'll go back. Equal norm of A to the power m 1 over m, 1 minus ln over n. So keep in mind that since n is bigger than m, and ln is between 0 and m minus 1, so ln of n is less than 1, and therefore the power is positive, and then this is less than m1 over n r plus epsilon r of a. To the power 1 minus ln of over n. So if we let, because this is true for any n bigger than m, okay, and since ln over n is bounded between 0 and m over n, so if we let n go to infinity, let n go to infinity, we get the lim sup of the nth root of the norm of a to the power n is less or equal than 1, because m to the power of n goes to 1, and r of a plus epsilon to the power 1 when n goes to infinity. So r of a, which is the infimum, is less than lim inf of the nth root of norm of a to the power n when n goes to infinity, okay, less than lim sup nth root of norm of a to the power n, and this is less than r of a plus epsilon. N goes to infinity. So you see, since epsilon was arbitrary, we get that lim inf when n goes to infinity of the nth root of norm of a to the power n equal lim sup of the nth root of the norm of a to the power n, equal to r of a. So the limit exists, okay, so limit exists, so r of a is in fact the limit of the nth root of the norm of a to the power n. So this limit exists here for any bounded operator a. Interesting. So that's known as the spectral radius. So now assume that r of a is less than 1. Okay, let alpha belongs to r such that r of a is less than alpha less than 1. So there exists n0 such that for every n greater than n0, we have nth root norm of a to the power n is less than alpha here. Okay? Or the norm of a to the power n is less than alpha to the power n. Okay. Let's make it a little bit, we don't need to be, because otherwise, I mean, it doesn't make a difference, but because we can take another number bigger than alpha, but we can still make it less than alpha, okay? What we need is to be away from 1. That's the whole point here. So, since alpha is less than 1, then the series a to the power n from 0 to infinity is absolutely convergent. Absolutely convergent. Okay, and then for that, we need to use the fact, in order for us to say it is convergent, we need the completeness of BU. And for that reason, we are going to need U to be complete. So here, okay, no, we are going to need a Banach space. So U must be a Banach space to give BU the structure of Banach space, and therefore now we're able to say that so sigma of a to the n from n equals 0 to infinity belongs to B. Okay, the calculations before, we have done it. We can do it again, and we can show that this exists, okay, and I minus A inverse is equal to sigma of a to the n from 0 to infinity. Okay, so this improves on the previous result when the norm of a is less than 1. Okay, and in general, okay, remark, okay, same proof that if r of a is less than absolute value of lambda for some lambda in R, then we have that's 1 over lambda sigma of 1 over lambda to the power n, a to the power n, n from 0 to infinity is convergent. Same proof. Okay? And we get that lambda I minus a, as we did before, the inverse exists and is equal to 1 over lambda n, a to the power n from 0 to infinity. Okay, note that though this theorem improves because r of a is less than the norm of a, okay, so these two results are improvement to the previous one, improvement. We still have a problem, a major problem in fact, a major problem of finding r of a. This is not an easy task. So yeah, it improves, but it's still not easy to find the radius, spectral radius of an operator A, R of A. Let us finish this lecture on bijections and invertible operators by a final remark. Let A be in B UV such that A inverse exists, okay, and A inverse is bounded. Okay? Okay, note that the norm A inverse A U, okay, so keep in mind U belongs to U, A of U belongs to V, A inverse belongs to U. So this is the norm, and this is equal to the norm of U. And this is less than the norm of A inverse because we said it's bounded, the norm of AU, but this one now is in V, okay? So 1 over norm of A inverse norm of U in U is going to be less than the norm of AU in V for any U in U. So what's interesting here is that this inequality, in other words, under the assumptions that exist, so what it means, so in other words, we have the existence of C positive such that C times the norm of U in U is less or equal the norm of U in V. These kind of maps, they have a named definition. Okay. The operator A, which is linear on UV, is called bounded below if and only if there exists C positive such that for every U in U we have C norm of U in U less or equal norm of AU in V. So this is the definition. And you see why we can talk about this. As I'm not assuming now that A inverse exists. If A inverse exists, we know that's bounded below. I'm talking about just a linear operator which is bounded below. Okay? So now it is easy to check that number one, if A is bounded below, then the null space, so then A is injective. Okay? Meaning that the null space of A is reduced to 0. Okay? And this is very easy because if A of U is equal to 0, then C times the norm of U is equal to 0, therefore the norm of U is equal to 0, therefore U is equal to 0. So the null space is reduced to 0. Okay? So now, if we restrict A, as we said earlier in the introduction, okay, if A is bounded below, then the map A, which this time goes from A to A of U, not to the entire space, is a bijection. So it is invertible. Okay? Now, let me call it not A, A hat, just to differentiate, okay? So A hat inverse exists, right? And it's easy to see that A hat inverse of V A hat inverse will go from AU into U, and AU is a subspace of V. Okay, so A hat inverse of V, okay, V belongs to V and this belongs to U. Okay, so this is equal to certain U, and what's the definition? What's the relation in U? And here we have A hat of U equals to V, or A of U equals to V. Okay? Good. So clearly this is less by the properties of being bounded than 1 over C, the norm of V in V, for some C positive, and it depends only on A, because it's bounded below. Okay? So clearly this tells us that A hat inverse is bounded from A of U into U, okay? And its norm, A hat inverse, is less or equal than 1 over C. Okay, so if we put all this together, we get the theorem. Let U and V be two normed vector spaces. Normed vector spaces. Okay. Let A belongs to LUV, which is bounded below, Then A is injective, and A going from U into the range of A is invertible. Okay? So, and, okay, moreover, A inverse, which goes from R of A into U, is bounded. So these are all the theorem here. It has all the information of what we discovered. Let's take an example of this, example of such map. Okay? Let A be a bounded linear operator defined on a vector space U. Then for any U in U, okay, we have the norm of AU, which is less than norm of A, norm of U. Since we have the same space, I did not put the norm of in U or in V. There is no V here. V is the same as U. Okay? It goes from U to U. Okay. Now, let lambda be a real number such that absolute value of lambda is bigger than the norm of A. Then we have the norm of lambda I minus A of U equal norm of lambda U minus A of U, which is greater or equal the norm of lambda U minus norm of AU. This is just property of the triangle inequality here used on the norm, which is equal lambda norm of U minus norm of AU. Okay, and since the norm of AU is less than the norm of AU, then this one will be bigger. So this will be bigger lambda norm of U minus norm of A norm of U, which is equal to lambda minus norm of A time norm of U. So if lambda absolute value, I'm sorry, this is absolute value. I'm sorry, absolute value. So if absolute value of lambda is bigger than norm of U, then the operator lambda I minus A is bounded below. Thank you very much, and hope that you enjoyed this web note or this lecture on invertible operators.